Hello and welcome to the last lesson in this unit, Precipitation Reactions. Precipitation reactions. Sometimes when two aqueous solutions are mixed together, a solid is produced. This solid is called a precipitate. The reaction is known as a precipitation reaction. We can use our knowledge of solubility to predict whether a precipitate will form. For our discussion here, you will need to have a solubility table handy. Before we can predict whether or not a precipitation reaction will occur, it is useful to review a category of chemical reactions called double displacement or double replacement reaction. In this type of chemical reactions, we will predict what will happen when solutions of two ionic compounds are mixed. If any reaction occurs, the positive cations will exchange places. Just want to show you, this is what an example of a solubility table looks like. It just gives you solubility rules to tell you if a substance will be solid. So here's our first example. So we have ZnBr2 in aqueous solution and two AgNO3s in another aqueous solution will give us ZnNO32 plus 2 ABr. Now we don't know if either of those are going to be solids, and the only way this reaction will occur is if one of them is a solid. So we need to keep in mind that our reactants, ZnBr2 and the AgNO3, are present as solutions. That means that the ZnBr2 is really a shorthand for writing the zinc ions and the bromine ions, and the AgNO3 is really shorthand for writing the silver ions and the NO3 ions. It is important that you understand that Zn2 and Br- are ions and are not joined together in a solution. They are separate from one another and present as separate ions rather than a single molecule or formula unit. The same is true for the AgNO3. The Ag plus and the NO3- ions are present as separate ions, not bonded together. So they're all just kind of floating around, happy-go-lucky, all by themselves. It is possible for these two solutions to mix together and every ion remain in solution as separate ions. If this is the case, then no reaction actually occurs. Now we just have one solution with four separate ions present. But if we look at our solubility table, we see that Ag plus and Br- form an insoluble compound. These two ions will find each other in the solution and form an insoluble precipitate, a solid. Okay, so we'll just look at our solubility table. If I can put it somewhere. Okay, so we are looking at silver and bromine. Okay, so if we're looking here, okay, so here's our bromine. Okay, all chlorides and bromides are soluble with the exception of silver. Okay, so that tells us that the two of them will find each other and be pulled out of solution. To the side. This occurs because the attraction between the Ag plus and the Br- ions is stronger than the attraction between the separate ions and the polar water molecule of the solvent. This is essentially what insolubility means. So they want to be together more than they want to be with the water. On the other hand, we see in our solubility table that Zn2 plus and NO3 forms a soluble compound. Thus, these two ions will remain in solution, not really forming a compound at all. The attraction between the polar water molecules and the Zn plus and NO3- is stronger than the attraction between the Zn2 plus and the NO3-. This is what soluble means. So if I pull this table back in here, okay, so our Zn and the NO3- is NO3-, all nitrates are soluble right at the top here. Okay, all nitrates are soluble, so it's going to remain in solution. All right, we now return to our double displacement reaction and add the physical states to the two products. Okay, so we have at the end there, we have the ZnNO3. Remember, all nitrates are aqueous, so it's going to stay as an aqueous. And the silver bromide is a solid because it forms the precipitate. To get a clearer view of what really occurs during this reaction, we will write our solutions out in the long form rather than the shortcut. Remember, anything that is aqueous is really present as separate ions. This, however, only applies for aqueous states. Thus, we can rewrite our equation as the following. So the zinc 2 plus the 2Br minus plus 2Ag plus 2NO3 minus gives us zinc 2 plus 2NO3 minus plus 2AgBr solid. Notice that some ions are the same on both the reactant and the product side of the equation, indicating that they did not undergo any change during the reaction. They were present but did not participate. Ions that are present in a reaction do not participate are called spectator ions. Sometimes we remove spectator ions from the equation in order to highlight what changes actually occurred during the reaction. The reaction in which the spectator ions have been removed are called net ionic reactions. So therefore, our overall reaction, we're going to look and we're going to figure out which two ions are the same on both sides. So the zinc's the same and the NO3 is the same. So those both get removed and we end up with our net ionic reaction. Well, what does this mean? Let's look at what happens when we mix a solution of MgCH3COO2 and NH42SO42. Begin by writing a balanced equation predicting the products of the double replacement reaction. Later we will predict the physical state of the two products, but we know that their reactants are both aqueous solutions. Okay, so we're just going to predict, so we switch places. So the Mg switches with the NH4 and the NH, and then those switch. So we end up with those products. Next, we're going to refer to our solubility table to determine whether either or both of the two products will form insoluble precipitates. Okay, on our solubility table, we find that both the MgSO4 and the NH4CH3COO are soluble compounds, meaning they will remain in solution and not form precipitates. Thus, there is no reaction occurring since all participants simply remain in solution. Separating ions. The knowledge of precipitation reactions also allows us to selectively use selective precipitations to separate mixtures of ions. For example, we have a solution that contains the following cations: silver, copper, and magnesium. Of course, it isn't possible to have a beaker full of ions, just cations, which each has to be associated with a negative anion. For argument's sake, let's say these cations are all associated with the nitrate ion NO3-. Nitrate ions are useful too, since compounds containing nitrates are always soluble. So we really have a mixture of silver nitrates, copper nitrates, and magnesium nitrates. The nitrate ions will remain as spectator ions, so we will not need to consider them further. We wish to isolate each ion by causing one at a time to precipitate out of solution. Once a solid precipitate forms, we can filter the solid precipitate out, leaving other ions in solution. We are given the following solutions to use: sodium sulfate, sodium chloride, and sodium hydroxide. As with nitrates, you should begin to recognize that the sodium ions, the Na, will also form soluble compounds. So the sodium will remain as a spectator ion, which we can ignore. Thus, we are really given solutions of anions, this sulfur, chloride, and hydroxide. We will be adding these one at a time to our cation mixture. We need to determine the order which we can add the solutions, so we only have one precipitate occurring with the first addition. This will remove one of the cations from solution. Then we can continue until all the cations are isolated from each other. So what we're going to do is we're going to set up a table with our cations at the top and our anions down the side. Then we're going to use our solubility table to determine which combination produces a soluble compound and which will form, or which one will have low solubility. These are the ones that will precipitate out. So we're going to use PPT as the shorthand for precipitate, and SOL for the shorthand of soluble. Pull this out here. Here we go, and I can see both. All right. So, first we'll look at silver and sulfur. So silver is sulfur. Okay, so S2. So all sulfides are insoluble except those of Na, K, NH4, and alkaline earth metals, Mg2+, Ca2+, Sr2+, and Va. Also sulfides of Al and Cr hydrolysize and precipitate as corresponding hydroxyls. Alright, so all we really have to worry about is this tells us that this will precipitate, okay, because remember all sulfides are insoluble except for these ones. This one will remain soluble. Okay, now we're going to look at the chlorines up here. Okay, all chlorides, bromides, and iodides are soluble except silver, lead, and mercury. Okay, which means this will precipitate, this will remain soluble, and this will remain soluble. Okay, finally, we need to look at the hydroxide, which is right here. All hydroxides are insoluble except for that of sodium and potassium. Hydroxides of Ba and Ca are slightly soluble. So all hydroxides are insoluble, and we don't have any of those exceptions, so all of these are going to precipitate out. Okay, so now we have to figure out in what order are we going to add in our other solutions to one at a time precipitate out our positive ions. So we need to determine the correct order for adding the negative ions. We need to be very careful with this next step and be sure we read the chart in the right direction. If we add the S2 first, we will get two cations to precipitate, the Ag plus and the Cu2+. This would not help us, as they would still be mixed together, this time as a solid. Adding the OH minus first would be even worse. All three cations would now be mixed together as solid precipitate. Only by adding the Cl minus first can we separate out one of the ions, the silver. The others would remain in the solution. The formula of the first precipitate would be AgCl solid. As it is important to realize that while both the S2 minus and the OH also form precipitate with Ag, once it has been removed with the Cl, we no longer need to worry about it. It's all gone. Once we've added the Cl, we've removed the Ag from solution. So if we add the S2 minus, we again form a single precipitate, the copper sulfide. solid, thus removing all the copper from the mixture. This will leave us with the Mg2+, still in solution. Sometimes this last cation is allowed to remain in solution, but if we choose to add OH to produce our final precipitate magnesium hydroxide, the solid. Alright, I hope you enjoyed this lesson, and we will see you tomorrow in class.